Hello and welcome to Shri Tech Education YouTube video channel. In today's lecture, we are going to study how to find out the natural frequency of free torsional vibration of two rotor system, and also we will study how to find the length of torsionally equivalent shaft. We will solve problem based on these two also. Let us start. Before starting this, previous to this video, we have studied how to find the natural frequency of free torsional vibration of a single rotor system. That thing we can study, or you can study on the link given in the description, as well as at the top right corner one suggestion link is given. Click on that, watch that video, and you will get how to find the natural frequency of free torsional vibration of single rotor system. In that, we have got the formula for this natural frequency of single rotor system as Fn is equal to 1 upon twice pi square root q by I, where q is torsional stiffness and it can be given as Gj by small l, where capital G is modulus of rigidity of shaft material, J is polar moment of inertia, it is equal to pi by 32 d raised to 4, where d is diameter of shaft, L is the length of shaft, and I is the mass moment of inertia of that disc or rotor in kg meter square. It can be found is equal to mk square. K is radius of gyration of that disc. Now, we have also studied that for a single rotor system, one end of that shaft is fixed, another end of shaft connects with one rotor. Now, for that we have drawn a vibration amplitude diagram also. In that, one point is called as a node at which amplitude of vibration is 0, and that point is a or a fixed point where shaft is fixed, and at the free end the amplitude of torsional vibration is maximum. That we have studied for a single rotor system. Now for two rotor system, we will find out the natural frequency. Now consider a two rotor system as shown in this diagram, where A and B are the two rotors connected at the two ends of this shaft, and that shaft is mounted in between the two bearings so that that shaft can freely rotate. And if I rotate A disc and B disc in opposite direction, exactly equal torque, but in opposite direction, if I apply on A and B disc and release, then it will twist and untwist continuously in opposite direction alternately, so that it will create a torsional vibration in the shaft. So at that time we have to find out the natural frequency of this shaft, and it is necessary to find the natural frequency of torsional vibration to avoid the resonance, so that the failure of the system can be avoided. Now consider this A and B discs are connected by the shaft of length L. Let the IA be the mass moment of inertia of A disc in the kg meter square, IB be the mass moment of inertia of the rotor B, G is modulus of rigidity of shaft material, J is polar moment of inertia which can be found by pi by 32 d raised to 4, where d is diameter of shaft, L is the length of shaft. LA and LB are the lengths of part PN and NQ. Now distance of node point from rotor A, that is distance PN, is, we are calling it as a LA, small l in suffix A, small LA, whereas distance from node point to point or to second rotor, that is B rotor, that distance is NQ, and we are calling that distance as a small lb. Now in single rotor system, we have found one node point at the fixed end. Here we are finding that node point in between the two rotors, and that exact distance we are not knowing. We are going to find out that distance, that is LA and LB distance, that is position of node point, we are going to find out. But what is node? We have studied previously also. The section of the shaft whose amplitude of torsional vibration is 0 is called as a node. At that point the vibration amplitude is 0. Now if I twist and untwist these two discs A and B alternately, then there will be formation of one point called as a node point, where amplitude of vibration is 0. It will not vibrate at all. So in this derivation we are going to find out the position of that node point as well. That means small LA and LB distances as well. Now to find out the natural frequency, we are applying the torques on A and B disk exactly similar. That means magnitude of the torque is similar. Therefore, the vibration amplitudes or vibration for disk A and disk B will be same. That means the total vibration of system will be remaining same. This is the condition given, or we have to assume. Now in this case, now if node point is created at certain distance from A disk and at certain distance from B disk, then we can assume from node point to disk A as a one rotor system, and from node point to disk B as a another one rotor system. And we know the natural frequency of torsional vibration of one rotor system. For rotor A, it is equal to Fna is equal to 1 upon twice pi square root Gj by LAIA. Gj by LAIA. This we will call it as a first equation. For second rotor, that is B rotor, from node point to rotor B, again we will consider one rotor system, and the natural frequency of that is equal to Fnb is equal to 1 upon twice pi square root Gj by LBIB. Capital G and J will remain same because diameter of that shaft is same, as well as modulus of rigidity of the shaft material is same. Therefore, we get the two equations, natural frequency for rotor A and natural frequency of rotor B for torsional vibration. Now we have assumed that Fna is equal to Fnb. That means the torque applied on A rotor and B rotor are same, therefore these both rotor will vibrate with the same frequency. Therefore I can write Fna is equal to Fnb, put the values of formulas. Fna is equal to 1 upon twice pi square root Gj by LAIA is equal to Fnb, that is 1 upon twice pi square root Gj by LBIB. Cancel out the terms and remaining term, call this equation 3, that is IALA is equal to IBLB. Then we can write in terms of LA is equal to LB into IB upon IA. LA is equal to IB upon IA into LB. Now third equation we have got as a LAIA is equal to LBIB. We know that one more equation, that is total length of this shaft, can be written as L is equal to LA plus LB. That means position of node point from disk A and position of node point from disk B, LA plus LB is equal to small l. Call this as equation number 4. Now observe carefully, in equation number 3, equation is in terms of IA and IB and LA and LB, whereas equation 4 is there which is in terms of LA and LB, where total length L is known. In equation 3, IA and IB values we are knowing, or we can find out. Then these two equations are in terms of lengths, that is LA and LB. Solve these two equations to find out the lengths LA and LB. Then these are the positions of node point. Once the position of node point is known, substitute these values of LA and LB in equation 1 and 2. Previously we have written equation 1 and 2 for the frequency formulas. Put in these frequency formulas, we will get the values of natural frequency of torsional vibration of two rotor system. That is the method to find out the natural frequency of two rotor system. What we have done, we have assumed the two rotor system as the two independent single rotor systems, and the frequency for these single rotor system, that is Fna is equal to Fnb. We have got the equation number 3 as LAIA is equal to LBIB, and we are also knowing that L is equal to LA plus LB. Solving these two equations, we have got the values LA and LB, that is position of node points, And putting these values of LA and LB in the equation 1 and 2, that is, we have got the frequencies of torsional vibration of these rotors. That is nothing but a torsional vibration of system. Now this is for two rotor system, but in actual practice that shaft is not having throughout equivalent diameter or throughout same diameter. In actual practice that shaft is having some different diameters for different lengths, just like in this diagram I have shown. A diagram, shaft of varying diameter. Now first L1 length it is having diameter D1, second L2 length it is having diameter D2, third L3 length it is having diameter D3. All these three diameters are different and two rotors are connected to their two ends. At that, in this case we have to find out the natural frequency, but first we need to convert this shaft into torsional equivalent shaft by changing the diameter throughout same diameter, and it will change the length of this shaft. Now we will do this we will do by some derivation. Now consider a shaft of varying diameter as shown in figure A. Let this shaft is replaced by an equivalent shaft of uniform diameter D and length L. These two shafts must have the same total angle of twist when equal and opposite torques are applied on these opposite ends. Now suppose I have applied the torque T clockwise on one rotor and anti-clockwise on one rotor, then it will be distributed or it will be divided into all the shafts of varying diameter equally. That means I can write the total angle of twist theta is equal to theta 1 plus theta 2 plus theta 3. That is, total angle of twist of shaft is equal to sum of angle of twist of different lengths. Sum of angle of twist of different lengths. That is, I can write theta is equal to theta 1 plus theta 2 plus theta 3. Now this theta I can write as tau by L upon tau by L upon G into J, because we know that tau by theta is equal to Gj by L. Same we have rearranged it as a tau into L divided by G into J. For theta 1 I can write tau into L1 divided by G into J1 plus tau into L2 divided by G into J2 plus tau into L3 divided by G into J2. Now cancel out this torque because torque is same we have applied on the all throughout this shaft. G will also cancel out. G is modulus of rigidity. It will same for shaft material. Remaining will be L by J is equal to L1 by J1 plus L2 by J2 plus L3 by J3. Now remember D1, D2, D3 are the diameters of length L1, L2, L3. J1, J2, J3 are polar moment of inertia of the shaft for diameter D1, D2 and D3. Theta 1, theta 2, theta 3 are the angle of twist for the length L1, L2 and L3. Now in this equation of L by J, we will put the value of J, that is polar moment of inertia, as pi by 32 d raised to 4. By putting these, for J1 it is pi by 32 d raised to d1 raised to 4. For J2 it is pi by 32 d2 raised to 4, like this. Now cancel out the terms which can cancel, that is pi by 32 will get cancelled and remaining will be L by d raised to 4 is equal to L1 by d1 raised to 4 plus L2 by d2 raised to 4 plus L3 by d3 raised to 4. Now it is assumed that the diameter of torsionally equivalent shaft is equal to one of the diameter of actual shaft. That means in B diagram, whatever equivalent diameter I have written D, it is equal to D1. That means one of the diameter of actual shaft. Now you can assume this D is equal to D2 also, or you can assume this D is equal to D3 also. I am assuming this D is equal to D1. always you can assume this d is equal to d1 also, no problem at all. Now here, if I assume this d is equal to d1, that means torsionally equivalent shaft diameter d is equal to d1. Therefore this equation will change as L by d1 raised to 4 is equal to L1 by d1 raised to 4, remaining will be same. Now shift this d1 raised to 4 on right hand side, you will get value of L. L is equal to L1 plus L2 into d1 by d2 raised to 4 bracket raised to 4 plus L3 into d1 by d3 bracket raised to 4. This will be formula to get the length of torsional equivalent shaft L, and it is equal to L1 plus L2 into d1 by d2 raised to 4 plus L3 into d1 by d3 raised to 4. This is the formula to find out the length of torsional equivalent shaft, and it is necessary, that is prior step, to convert the varying diameter shaft into torsionally equivalent shaft. Then you can find out the natural frequency of two rotor system. Now we will solve one problem based on that, so that you can understood whatever we have studied up till now. Now I will read the problem. A steel shaft of 1.5 meter long is 95 mm in diameter for the first 0.6 meter of its length, 60 mm in diameter for the next 0.5 meter of its length, and 50 mm in diameter for the remaining 0.4 of its length. That means one shaft is given of varying diameter, 0.6 meter length has 95 mm diameter, 0.5 meter length has 60 mm diameter, and 0.4 meter length has 50 mm diameter. Now I will read next problem. The shaft carries two flywheels at the two ends. The first having a mass of 900 kg and 0.85 meter radius of gyration, located at 95 mm diameter, that is on left side, and the second having mass of 700 kg and 0.55 meter radius of gyration, located at the another end, that is on the right hand side. Determine the location of the node and the natural frequency of torsional vibration of system. That is, you have to find out the location of node. For two rotor system, always remember there will be only one node point will be generated, and that will be in between the two rotors. That we have to find out. That means if A and B disc are there, that is LA and LB distances we have to find out the node point. And next we have to find out is natural frequency of free torsional vibration. It is given that modulus of rigidity of shaft material is 80 giganewton per meter square. First write down all the given data in the problem. Draw the diagram from given data so that three lengths with the three varying diameters, and at the two end A and B discs we can assume. Then first step to solve this problem is to convert the different diameter shaft into torsional equivalent shaft having a single diameter, and we will assume this diameter D is equal to D1. That means it is equal to 95 mm. If we are going to convert it, then the length of this shaft is going to change, and we can find out this torsional equivalent shaft length by one formula just we have derived, that is L is equal to L1 plus L2 into D1 by D2 raised to 4 plus L3 into D1 by D3 raised to 4. Put in this formula the values. L1 is equal to 0.6 meter plus L2 is 0.5, D1 is the 95 mm converted into meter divided by D2 60 converted into meter raised to 4 plus 0.5 into D1 by D3 bracket raised to 4, and we will get this length after calculation as 8.95 meter. And in second diagram I have shown there a shaft with a diameter 95 mm and with a length 8.95 meter length. Now we can find out the natural frequency by after finding this length, we will find out first the node point position, that is length LA and LB. Assume length LA from node point to A disk, and from node point to B disk assume distance as LB. Then for location of this node, we know that IALA is equal to IBLB. Then find the value of IA and IB and put in that equation, where IA is equal to MK square. For IA, MA KA square. Put the value of mass of disk A, radius of gyration of disk A in meter. We will get value of I in kg meter square. For disk A it is 650 kg meter square. Similarly, find for disk B, that is MB kb square. Put this value of I and IB in the first equation of IALA is equal to IBLB. We will get IA value in terms of LB. We will get value of LA in terms of LB, and we have got this LA is equal to 0.32 LB, 0.326 LB. LA is equal to 0.326 LB. Now call this as equation 1. We also know that LA plus LB is equal to L, and total L of torsionally equivalent shaft length we are knowing that is 8.95, and LA, whatever we have found previously, LA is equal to 0.326 LB. Put in the equation below, then we will get 0.326 LB plus LB is equal to 8.95. Solving this, we will get LB value as 6.75. Put this LB value in the above equation of LA plus LB is equal to 8.95. We will get LA is equal to 2.2 meter as well. Do this calculation by pausing the video once again and check whether the LA and LB values are getting same or not. This is the location of node point. Once this LA and LB values are known, that is location of node point is known, you can find out the natural frequency of free torsional vibration by formula Fna is equal to 1 upon twice pi square root Gj by LAIA. Now values of G is given, J is given, J is not given, G is given, LA we have found, IA we have found, value of J is not known. To find out Fna, first find out the value of J. That can be found by pi by 32 dA raised to 4, whereas diameter of A is 0.095. Put the value and we will get the J value as 18 to 10 raised to 6 meter raised to 4. Put this value in equation of frequency, we will get natural frequency Fna is equal to 3.37 Hertz. Pause the video and do the calculation once again. You will find the natural frequency as 3.37 Hertz. Like this, we are going to find out the natural frequency of torsional vibration. First, always you have to convert the different diameter shaft into same diameter shaft by using this formula of equivalent length. Then you have to find out the location of node points. Then that is the value of LA and LB, and then we have to find out the natural frequency of free torsional vibration. We know Fn is equal to Fna is equal to Fnb. Either Fna you can find out or Fnb you can find out. Both you will get the same values. Now one more problem I have given for your homework. Pause this video, read the problem carefully and find out the answer for the position of node point and the frequency of torsional vibration. Comment in the answer box comment the answers in the comment box for position of node and frequency of torsional vibration. Thanks for watching my video. Subscribe the channel if you are not subscribed. Press on the bell icon so that you will get the next subsequent videos on this vibration chapter. Thanks for watching.